Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and today is the first class of physics in the series Masterstroke, where we are discussing all the chapters in one shot. So today I am going to discuss electric charges and fields, very important chapter in terms of KCET. Also this is an important chapter for your PU board. If you have not done this chapter, this is a must do chapter, very important, right? At least 4 to 5 question comes from this chapter, and today we are going to see through all the important topics, all the important concepts from this chapter. So at the beginning of this series, let's see what are all the important concepts from this chapter. This is only the important concept, not the entire chapter, but the key concepts that you have to study if you are studying it just before your KCET exam. So what are all the important concepts? Electric charge and properties of electric charge, obviously very important. Then we have Coulomb's law, another important concept. Then we have electric field lines, okay, properties of field lines. These are also very important concept from this. Then we have electric dipole and dipole moment, electric dipole, electric field due to dipole, okay. So these are all important. Electric dipole itself is very important, okay. From there we have electric dipole on the axis, electric dipole on the perpendicular bisector, we have electric dipole in an external field. So these are all the important part. Next we have electric flux and Gauss's law. So electric flux, sometimes they might ask you to calculate the electric flux. Sometimes you have to use Gauss's law to calculate electric flux or the electric field for the matter. So these are all the important concepts from this chapter. This is must before you appear for your KCET exam. You cannot ignore any of these important concepts. Now we have slight time, so we will explore the chapter in detail. This is a one-shot video. Entire chapter will be covered if you watch this. So first we will start with electric charge, right? So we know there are a few things about electric charges. So here we have listed down all the important things that you have to remember about electric charge. What are those? So there are two types of charges. What are the two types of charges? Positive and negative, right? Positive charge, negative charge, simple. Next, like charges repel each other, we already know, and unlike charges attract each other. So don't get confused. Unlike charges attract, like charges repel. So two positive charges will repel, two negative charges will repel, whereas positive and negative, they will attract. Now next, in a neutral object, positive and negative charges are balanced. So if I say a neutral object, that does not mean it is void of charges. That means it does not have any charges. It has charges, but equal number of positive and equal number of negative charges are present, okay. What else? To charge a neutral object, we need to add or remove one type of charge. So if we want to charge a neutral object, basically if we say that this is positively charged or this is negatively charged, only one type of charge can be added or removed, okay. Only electrons can be added or removed. So the one type of charge is nothing but electrons. This one type of charge is nothing but electrons. Only you can add electron. If you add electron, it becomes negatively charged. If you remove electron, it becomes positively charged, okay. Electrons are negatively charged. Obviously we know that if electrons are added to a body, it gets negatively charged. If electrons are removed from the body, it becomes positively charged. This is not negatively, this is positively, right? Now point charge, from here we also have another definition of point charge, which is very important. We have seen that in many cases we have seen that. So this is positively, right? We have seen point charge is placed, point charge is placed. What is a point charge? So point charge is basically when the size of the charged object smaller compared to the distance. So whenever we say this is a charged object, okay, and if this is the distance, say r, okay, if the size of this object is smaller compared to the distance, then we say this is a point charge. Exactly point is obviously not possible. So in physics we do this approximation. So suppose for example the size of the object, say of 2 millimeter, and distance say 1 meter. Now millimeter is 10 to the power of minus 3. So the distance is 1000 times bigger than that of the size of the object. So here we will say that size of the object is very small compared to the distance we are covering. So that's why we will say this is a point charge. Okay, maybe it is in the micrometer or millimeter, does not matter. If the distance is long enough, then we can consider it to be a point charge. So point charge is not exactly a point theoretically. Practically speaking, theoretically it is yes, it is a point. Practically speaking, they have their size is very small compared to that of the distances. That is the meaning of point charge. Even though not super important, but it is very relevant when you start looking into this concept. Now next, move on to the part where gold leaf electroscope is a device that can measure the presence of charge. Gold leaf electroscope is shown here. This is a device that can measure the presence of charge. So if the object is neutral, object is positively charged or negatively charged, that can be determined using this device, which is called gold leaf electroscope. Okay, SI unit of charge is obviously Coulomb, and its dimension is ampere into time, or current into time. Its dimension is current into time. Current is considered to be a fundamental dimension, right? We know there are 7 fundamental dimensions, so current is one of them, and current's symbol is represented by A. So A into T is the dimension of charge. So now basic properties of electric charges. Charges are additive in nature. We already have studied these things in our PU class, but again we have to look into in little bit detail. So what is that? Charges can be added algebraically. What is the meaning of algebraically addition? That if you have few charges, you just simply take the values and add them like you are adding few numbers, right? So if it is plus, it will be plus. If it is minus, it will be minus. Just like a normal addition that you have done in your class 5th, class 6th, maybe class 4th grade. Similar addition you are doing. Okay, nothing new, nothing, no rocket science. Next is charge is a scalar quantity. Obviously this gives the fact that charge is a scalar quantity. You just need to add their values along with the sign, right? If it is a scalar quantity, we can add them using the values and their sign, right? So simply as that. Now charges are conserved. Conserved means what? Conserved means the total charge of an isolated system is always conserved. That means always constant. Okay, so if I say isolated system means which is isolated from the nature, which is not exchanging anything with the surroundings. Okay, so that can be considered to be an isolated system. For example, if you consider a fish bowl or a aquarium, the aquarium can be considered as an isolated system. Total number of fish inside the aquarium is constant, right? Unless one can be dead, one can be new breeds are coming into the thing, but total amount is constant, right? So that is what is said constant means. But in case of aquarium, the fish can lay some eggs and new fishlings can born from there. So total number of fishes is not constant in the case of aquarium. Okay, maybe someone is dead, you have to remove that dead fish. So total number of fish is not constant in that aquarium. But in case of charge, total number of charge, total amount of charge inside an isolated system is constant. So that is the basic difference between an aquarium and an isolated system consisting of charge. Okay, it is not possible to create or destroy the net charge carried by an isolated system, although the charge carrying particles may be created or destroyed. So suppose I have a neutral body. The neutral body suddenly decide, okay, I want to give away some electrons and I want to become an ion. I want to become a positive ion. Even though the positive ion is existing, even though there is a negative electron charge is there, okay, the total charge still is constant. Okay, individually charges can be created or destroyed, but total charge cannot be created or destroyed. Okay, individually extra charge can be can appear. Okay, for example, if you consider energy, from energy you can create electron and positron pair. Okay, electron and positron pair can create out of energy. Okay, so electron positron pair can exist, but total charge of electron is minus E, total charge of positron is plus E, so total charge will still remain constant, that is 0. Okay, now charges are quantized, very important concept. What is the meaning of quantized? We have gone through a lot of chapters. In the chapter atoms we have learned about quantization briefly, then dual nature of radiation and matter also we have learned about quantization. So first thing you have to remember that charges are quantized means basically you can have only a fixed amount of charge. Okay, everything else is basically multiple of that fixed amount of charge. That is the smallest possible charge. So for example, I always use this example that you visit a milk shop to buy a packet of milk. So the minimum size of the packet available is the 1 quantum. Okay, for example, I have taken this is the minimum possible size of the milk that can be sold to you. So this is the minimum size, that means this is the 1 quanta. Okay, now everything, suppose we want 2 packet, 3 packet, 5 packet, whatever is it, that has to be the even, that is multiple of integer multiple of this packet, right? You cannot go to a shop and say I want 1.5 packet of milk. No, it is not possible. If half liter or 0.5 liter liter is the minimum size, then you can say okay, I need 1.5 liter. 1.5 liter means 3 packets. Okay, but you cannot say I want 1.75 liter of milk. The shopkeeper will say no, either you buy 1.5 or you buy 2 liter, but I cannot give you 1.75 liter of milk, because that is not possible. Similarly, in case of charges also there is a minimum possible value. All the other charges are basically multiple of that minimum possible value. So here we have 3 packets of milk. 3 packet means 3 liters or 1.5 liter. That is the integer multiple of the number of packets, right? So here also all free charges are integral multiple of a basic unit of charge denoted by small e. What is that small e? Small e is basically any other charge object. If you have that charge can be represented by a integer multiple of ne. Now here n can be 0. N can be 0 means neutral object. N can be positive, n can be negative. Positive means positive charge, negative means negative charge. So all the charges, positive, negative, all the charges are quantized. So you might think okay, E represents the charge of an electron. So basically that is a 1.6 into 10 to the minus 19 Coulomb. So only negative charges are quantized, maybe positive charges are not. No, even positive charges are also quantized. Very good objective question, MCQ question, that only negative charges are quantized, positive charges are not. Is it true or false? Obviously it is a false statement. Positive charges are also quantized. Now let's look into the another important concept, Coulomb's law. So statement, the force acting between 2 point charge is directly proportional to the product of the magnitude of the charges. So suppose 2 charges Q1 and Q2 separated by a distance of r. We will see in a detail in a while, but directly proportional to the product of the magnitude of the charges. That means product means multiplication, right? So directly proportional to the product of the multiplication of magnitude of the charges, and inversely proportional to the square of the distance between the charges. So it is inversely proportional. Inverse means 1 by r square. Okay, these are all very common. Next, the force acts along the line joining the 2 charges. Very important. Okay, so whenever we consider 2 point charges, the force is always along the line, either in this direction or away from. Okay, but it will be always in the line joining the charges. It cannot be in any other arbitrary direction. These are not possible. It is always along the line joining the charges. Very important. Okay, nowadays a lot of assertion and reason based question comes, so you have to be prepared. You have to be careful about even simplest of the statements as well. Now let's see, we have 2 charges Q1 and Q2 separated by a distance r. So here we can say that the force is basically K Q1 Q2 by r square. Why there is a modulus sign? Why there is a modulus sign? Because in the statement, if you see, the statement states that directly proportional to the product of the magnitude of the charges. Very careful. So magnitude of the charges, the direction depends on the type of charge, what type of charge you are using. If both the charges are positive or both the charges are negative. If the charges are similar in nature, then the force is repulsive. So force will be repulsive in that case. If the charges are opposite in nature, they will attract each other. So direction of the force will depend on the nature of the charges. Based on what charge is given to you, you have to find the direction of the force, right? So that is a very, very important part. You cannot generalize it. It will have to depend on problem to problem, question to question. So here K is called Coulomb constant. Value is very important, 9 into 10 to the power of 9 Newton meter square per Coulomb square. Okay, and K also sometimes represented using this value. K is equal to 1 by 4 pi epsilon naught. Here epsilon naught is permittivity of free space or vacuum. Okay, free space or vacuum. So this is an alternative term for free space. Permittivity of vacuum is also correct. Permittivity of free space also correct. Free space means where nothing is there, right? And its value is 8.854 into 10 to the power of minus 12 Newton Coulomb square Newton inverse meter to the power minus 2. Now this value you do not need to worry about. It will be given to your exam sheet. In the first page they provide all the constants, but this one is what you have to remember, because that sometimes if you remember this value, it helps you to answer questions quickly while you are solving the numerical questions, right? Now force between multiple charges. Suppose we have one charge, say Q, and I want to find charge between say this is Q1. I want to find force on this charge due to multiple other charges, Q2, Q3, okay, Q4 maybe here, Q5, so multiple other charges. So how to do that? So there will be a lot of different directions of forces based on whether this is positive or negative, right? So first what Coulomb's law is saying, that we can find only the force between two charges, right? So suppose this force is force on 1 due to 2, right? This force is force on direction is not important anyway, okay, force on 1 due to 3. So what we have to do, we have to calculate individual forces due to all such charges. This is an application, okay. Numerical questions will come based on such concepts. So this is an abstract concept like this. So some cases it will be away from, some cases it will be towards, okay. So it is based on the nature of the charges. So F14, F15, F16, right? These are the forces. There can be any other number of charges. The total force on this, total force, whatever the total force, say F net, that will be vector sum of all the forces. That will be vector sum of all the forces. This is very handy. Especially they will not give you any discrete configuration. They will give you such, suppose they will be giving you a rectangular configuration or a triangular configuration. So that is very, very important. Okay. So the formula for this is force on F1, that is the net force acting on F1, is the vector sum of all the forces. F1I means F1, if you put I equals to 2, you will get F12. If you put I is equal to 3, you will get F13. So vector sum of all the forces acting on 1, that will give you the total force acting on F. Q1. That is the easy formula to remember. Just the concept, problems, application we will see in our live class. Now let's move on to the electric field. This is a very, very, very important concept, where from a force we are trying to define a field. Okay, if you remember in the first PU gravitational chapter, gravitational force was there, and there was something called gravitational field, which is existing everywhere. Normally a field means which is not you cannot experience it unless and until there is another thing which is which can determine it. For example, gravitation. The Earth's gravity is already there, but if we are not here, we will not be able to experience the Earth's gravity. So there has to be some other mass present nearby to experience the force of gravity, right? So what is that force? Force is basically K. We have taken two charges, capital Q and a test charge small q. The force between them according to Coulomb's law is given by Q by R square. We have taken the magnitude of the charges only. Now if you remove this charge, that's what I was talking about. If you remove this charge, is there any effect of this capital Q here? Is it anything left? So for example, Earth is present at this position, it is experiencing the sun's gravity, okay, but what is the space between may say Earth and Moon? So Moon is also experiencing some gravities, Earth is also experiencing some gravity, but what is the what about the region between Earth and Moon? Is there any gravity present or not? Is gravity zero there? So that for that you have to put something in between that place and see whether it is experiencing some gravity or not, right? Whether it is moving towards Moon, whether it is moving towards Earth, or it is moving towards Sun. So to test that, you have to put a mass over there to check whether the force is acting or not. So that thing is called field, even though it is not clear whether it is existing or not, but as soon as you put some extra charge at that point, it will experience some force. That force is called electric field. So let's see in detail. So what we have to do, we have to divide the force by the value of this test charge. So whatever is left on the right hand side is called electric field, right? So electric field is basically force per unit charge. So if the charge is 1, if you make this charge 1, then whatever force is experienced by that charge is called electric field. Very, very important. So here capital Q is source charge and small q is the test charge. So this is the formula for electric field. This is the expression for electric field. Now let's see, in other words, we can write this as 1 by 4 pi epsilon naught q by r square into r cap. So what is this? This is a vector quantity, and what is the direction of r cap? If this charge is positive, then r cap is away from, okay, if suppose this is positive charge. If this is a negative charge, say negative, then the direction will be towards the charge. Okay, I know on black screen red is not clearly visible, so I will use some cheating. Okay, so this is negative. If this is negative, then the force is towards. If it is positive, force is away from. Okay, and this is the direction for r cap, right? But electric field equation in normal value, in most cases you just need to use this value. Okay, K's value you already know, so you can use this equation. This is the most important equation from this chapter. Now the electric field due to a charge capital Q at a point in space may be defined as the force that unit positive charge would experience if placed at that point. Now that makes sense. If it is a unit positive charge and this is also a positive charge, it will be repelled, right? So that's why the direction is away from. If it is a negative charge, this is a positive charge, it will be attracted, right? Whenever we apply electric field, calculate electric field, we do not use the sign of the individual charges. What we do, we try to find the directions, and based on the directions we try to add them. We will see that. Okay, so alternatively, if a charge Q is kept inside an electric field E, then the force experienced by it is given by F is equal to Q into E. So now we have only an electric field. We do not know what is the source of this electric field. Somehow maybe an electric current, maybe some other things. We do not know what is the source of this electric field. Okay, we just know there is an electric field present in this region. So if there is an electric field present, if we put a charge small q in this region, it will be experiencing a force, and that force is given by Q into E. So first we started with Coulomb force. From Coulomb force we moved into electric field by dividing with charge. Now from the charge, from the field, now we are coming back to force again. Why? Because electric field, sometimes, as I said, the source may be there, may not be there. If there is no source, we do not know what is the source, okay, then electric field force on a charge makes a a lot of sense if we use the electric field concept. Okay, not always Coulomb force is applicable. For example, multiple charges thing. Okay, if we can calculate the electric field, then force will automatically be taken care of. So Coulomb force, even though it is handy, it is not always super useful, right? So the shortcut for Coulomb force is basically using electric field. Okay, now see one problem. A charged particle of mass m and charge q is released from the rest in an uniform electric field E. Neglecting the effect of gravity, the kinetic energy of the charged particle after t second is. So what we have done, we have a charged particle of mass m and charge q. So mass of the charge is m, we have a charge m, okay, and charge is q. We have released it in an electric field from the rest. Okay, so we are trying to find the kinetic energy of the system. So gravity is ignored, so we cannot consider the mg term because you will see in later part in your PU class that gravity is very weak compared to electric force. So we do not generally consider gravity unless it is extremely important to consider, right? If the mass is super big and charge is very low, in that case gravity is considered. Otherwise we do not consider gravity for small particles. Okay, so suppose the charge is q, mass is m, you placed it in an electric field. Okay, and you are trying to find the electric field is given by E. You are trying to find its kinetic energy, right? So first you have to calculate what is the force acting on this charge, right? So force is basically given by Q into E. Okay, force is given by Q into E. What is the acceleration? Now our old father of physics, Newton, he is in the rescue that acceleration is nothing but force divided by mass. So Q into E divided by mass is the acceleration. Okay, so what is the velocity after time t? Okay, after time t, what is the velocity? So velocity again, v is equal to a into t. That is the velocity. That is the formula for velocity. So velocity is q e t divided by m. This is the formula for velocity. Now what is the kinetic energy? Now we know. Now everyone knows. Kinetic energy is basically given by, let's not confuse. EK, sometimes student confuse what is E. E is electric field, right? So in this chapter for kinetic energy we will use only capital K. Okay, so kinetic energy capital K is half m v square. So they have said what is the kinetic energy, the charged particle after t seconds. So this is the kinetic energy after t seconds. So half m into v square. V square means this everything square. So q square, e square, q square, e square, t square, everything square divided by m square as well. Now there is one m in the top, one m in the division, so one of the m will cancel. So we can write this as q square, e square, t square divided by 2m. Okay, so it will be e square, q square, there is a mistake, it will be t square, not r. There is no r here, right? Yes, so there is a mistake here. So q square, e square, q square, t square divided by 2m. Okay, so as you can see, this is a medium question. What is the possible concept use? Concept uses electric field. What is the possible mistake that you can make? You do not have the enough concept knowledge to solve this question. Okay, this question is not only based on your current chapter, as you can see, it based on some of the concepts from your previous PU1 class as well. Okay, and expected time to solve this question is 1 minute. Okay, you can take 1 minute to solve this question. As you know, you do not need to solve the answer in in detail, because this is a KCET exam, not your PU board exam where you have to show all the calculations. So you can use all the shortcuts, all the if you want to jump some steps, if you are confident, you can jump the steps and you can solve it. But 1 minute, in my opinion, if you are starting it and if you can still solve it maybe in 2 minutes or 3 minutes, still fine. Okay, but once you have practiced this kind of questions regularly, you have to solve it in 1 minute. Okay, now let's move on to the next part, electric field, some key points about electric field. So the first point is the electric field due to a system of charge exists at every point in three-dimensional space. So even though we draw a two-dimensional diagram in most of the cases, okay, so for example, if I say this is Q, the force is like this or like this or like this, so whatever it is, you have to remember this is a three-dimensional thing. Okay, it exists in X, Y, Z, all possible direction. Okay, so if I say electric field, it is basically a three-dimensional thing. Okay, so the charge, it is kept here. Even though I am saying electric field at this point may be away from it, it can also exist like this, like this. Three-dimensional things are difficult to draw, but electric field is a three-dimensional field, very unique, right? Next, what? For a positive charge, the electric field will be directed radially outwards from the charge. So if the charge is positive, electric field is radially outward, right? We know that. Next, for a negative charge, the electric field vector at each point is radially inward. So if the field is negative, if the charge is negative, field is radially inward, right? Electric field due to a point charge is spherically symmetric. So if the charge is point, that is the size of the object is very small compared to the distance, then it is a spherically symmetric. What is the meaning of spherically symmetric? So suppose this is the charge Q. Okay, if you consider a sphere surrounding this charge, okay, such that this is the center of the sphere, then on the surface of this sphere, each and every point, the electric field, magnitude of electric field will be constant. Very interesting thing. We will see again in Gauss's law once more, but you have to remember that when the charge is point, and if you are trying to find electric field on the surface, and it is not only for any single radius. Suppose for radius R1, the electric field on the surface is E1, right? Now you are considering a different radius, okay, say R2. Now the electric field on the surface is E2. E2 will also be constant. Obviously E2 is not equals to E1, obvious reason, but for any other radius also, for all the concentric circles you can consider, concentric spheres you can consider, on the surface of the sphere electric field will be constant for a given radius. But for two different radiuses, radii, the values will be different. Okay. When a positive charge is kept inside an external electric field, it experiences a force in the direction of the external electric field. So if you keep a positive charge, in an external field, it experiences a force in the same direction as the electric field. Okay, positive charge experiences force in the same direction as the external field. When the negative charge is kept inside an external electric field, it experiences a force in the opposite direction of the electric field. Very important concept, these two. So when you keep an electron in the electric field, the electron experiences a force in the opposite direction of the electric field. That is why electron moves from higher potential to lower potential, right? So that is very important. Sorry, my mistake. Electron moves from lower potential to higher potential. We'll see that in next chapter, not today, but just a relevant information that electrons move opposite to that of the normal motion of the charges, normal conceptual motion of the charges. Now let's see, field lines start from positive charges. Now this is the properties of electric field lines. Another important part, field lines start from positive charges and end at negative charges. If there is a single charge, they may start or end at infinity. So if it is a single charge, okay, then starting point can be at infinity, So if it is a positive charge, the electric field lines can start at infinity. But if you have a negative charge, then always you have to remember that electric field lines always start at positive and end at negative. Okay, so field lines will always, suppose the one line was going like this, so it started at positive and it ended at negative. So no matter, okay, it can be a curved line, not necessarily it will be a straight line always. It can be a curved line, but they are always starting at positive, ending at negative. In charge-free region, electric field lines can be taken to be continuous curves without any breaks. So there is a positive charge, there is a negative charge. In between these two charges, there is no other charge, no third charge present. So in this region, the electric field lines are continuous line. Continuous means straight line, right? You have already learned about continuity in mathematics. No break. So there is no break. Suddenly someone came say, no, there is a break. That is not the case. Okay, there is no break. Break is not there. It is continuous line. Okay, so it is a continuous line. Now, let's move on to the next point. Two field lines can never cross each other, the favorite property for all of the students. Whenever there is a question for a PU exam that write 3 properties of electric field lines, this is the first point almost 80-90% students write. This is the favorite thing about the students. Two field lines can never cross each other. If they did, what will happen? Okay, if they did, the field at the point of intersection will not have a unique direction which is observed. What is the meaning of that? Suppose there is an electric field. There is another electric field. They are somehow saying we will not obey this rule and we will intersect each other. Then at the point of intersection, we know that one more important thing, that if you draw a tangent to the electric field lines, you will get the direction of the electric field. I think that point is missed in this description. So if you draw a tangent on a point on the electric field lines, you get the electric field at that point. Okay, direction of electric field. So electric field is a vector quantity. So vector quantity can have only one direction at a point. It cannot have multiple direction at one point. There is a different type of quantity that can have multiple direction at one point, but that is way beyond your scope right now. Okay, so only one quantity that can have one direction at a point, that is a vector quantity. So electric field is a vector quantity. It cannot have multiple direction at the point of intersection. So what will happen actually, if you keep two different fields close together, they will have to obey the law of superposition. Eventually they will give rise to a what I say, superposed field that will have only one direction. Okay, two different direction will not be there. They will superimpose and they will give you only one direction. Okay, that is the vector addition. So definitely they cannot have two directions. Next, electric field lines do not form any closed loop. So electric field lines, suppose this is a positive, this is negative. Okay, electric field will always start from positive, it will always go to negative. No possible way for electric field line to come from negative to positive. No, this is not possible. Okay, it is possible in magnets, but in case of electric field this is not possible. So basically they are open lines. Okay, closed means, what is the meaning of closed loop? Closed loop means it is going from here, then you are going back from here. So you are from your home to your college, from college to your home. So that is a closed loop, and that is you are doing every day. But electric field lines are not closed loops. They are from home, they are going to college, they are staying there, they are studying throughout their entire PU board. That is the thing. Okay, so they are very dedicated, they don't waste time. Now electric field is a free space. In free space decreases as we move in the direction of the electric field lines and vice versa. So if we say electric field line are represented like this, that means electric field is stronger here. Here electric field is stronger. So A, say EA, say EB, say EC. Okay, so electric field strength decreases as we move in the direction of electric field. Okay, so EA is basically greater than EB, greater than EC. This type of conceptual questions are common in KCET exam. Okay, so tomorrow I will show you one such question. In the tomorrow is my live in the direction of the electric field lines and vice versa. Okay, so if you move opposite direction, electric field will increase obviously. Now let's move to the electric dipole. Now electric field is completed. Now let's move on to electric dipole. Since it's in one shot, I will not waste too much time. So two equal and opposite charges separated by a small distance is known as electric dipole. So we have two charges plus q and minus q separated by a small distance 2a. We generally represent this distance 2a for our own convenience. Okay, and one common example of electric dipole is HCl, where you can see that we generally give a delta plus charge to hydrogen, a delta minus charge to electron. Okay, so they slightly their lone pair slightly shift towards the bond pair slightly move towards the chlorine atom, right, because chlorine has a higher electron affinity. So that is how you can assign, okay, they have a electric dipole moment. Similarly, this same happens for water, right? Oxygen has higher electron affinity, so it takes away the electrons as a custody of those electrons. Okay, we have shared the electron. Now because I have more electron affinity, you are giving the electrons to me. So that is how there is a permanent dipole moment present in water. That is why what it is called polar solute, right? Polar solvent, right? Now dipole moment is very, very important. Electric dipole moment is the product of magnitude of one of the charges and the distance between them. It is a vector quantity. Okay, so dipole moment is basically given by, first of all, the direction is from negative to positive. It's a vector quantity, and it is basically magnitude of any of the charges. Magnitude means value of any one of the charges times the distance between them. Distance is obviously 2a. Be careful, in some problems I have seen the distance itself was given, say 2a was given, say 5 into 10 to the power of minus 6 micrometer, suppose. So this is entirely 2a. Some students multiply an extra 2 to calculate the dipole moment, which is wrong. Okay, if the distance is given, the entire distance is 2a. Very, very careful about this term. Okay, don't make such mistake. N cap is the unit vector from negative to positive charge. So then n cap is from negative to positive charge. So dipole moment is basically a vector quantity pointing from negative to positive charge. Very, very important. Okay, thus the direction of dipole moment is from negative to positive charge. Let's move on. So this is the case for points on the axis. If all the points are on the axis, then electric field due to the dipole is given by E axis. EA is 1 by 4 pi epsilon naught 2p vector divided by r cube. Okay, so r is this distance. Okay, r is the distance between midpoint and the point of observation. This is the point where we are measuring. Okay, so this is the electric field at this point. Okay, and if you see, this is there is a p. P is already, we know what is p. Magnitude of p is 2a into q. Right, this is the magnitude. Also, if you see the direction of p, this is the direction of p. So this is the p vector, and this is the EA vector. If you see, p vector, that is negative to positive, and EA vector both are in the same orientation. So same orientation means the sign is positive here. There is no negative sign here. Also 2p by r cube, very, very important. If you consider the points on the equatorial plane, you will see that the electric field on the equatorial plane, EEP, is basically negative of p by r cube. Same value, only thing is there is a 2 missing here. There is an extra 2 here, but that is missing. But otherwise there is a negative sign as well. Why negative sign? Because in this case the electric field EEP is in this direction, whereas dipole moment is in this direction. So dipole moment and electric field are on the opposite direction. That is why there is a negative sign. The negative sign represents electric field and dipole moment are in the opposite direction. Also, if you consider the magnitude, you have seen that EA is basically twice of EP. right? EA is basically twice of EEP. So there is a 2 here, right? So if you multiply 2 here, you will get the magnitude of the axial thing. So this is also important. Sometimes some easy objective questions will come. Okay, so vectorially EA axial is basically negative of 2 EEP. Okay, so they are opposite direction, as well as it is twice, axial field is twice that of equatorial field. Okay, now another easy concept, that a dipole in an external field. So when you keep a dipole in an external field, we know that positive charge will experience as a force in the direction of field, negative charge will experience as a force in the opposite direction of field. That will result in a torque acting on the thing. So the torque is basically given by P cross E, that is P is sin theta. Now remember that here electric field is considered to be uniform, that's why the field is given by parallel lines. Okay, so if the electric field is non-uniform, so suppose the electric field is stronger on the positive side, okay, and it is stronger on the negative side and weaker on the positive side, then the force on the negative charge will be much more than that of the positive charge. So what will happen, the combination will also experience a net force. So if you consider the net force in this particular case, when the system is in equilibrium, system is in uniform field, okay, the force in this case, say F negative, and force on the positive charge F positive, magnitude wise they are equal. So magnitude wise F negative is equals to F positive. So the net charge is basically F plus minus F minus, which is equals to 0, right? But if the field is non-uniform, suppose the electric field is very strong near the negative charge and it is very weak near to the positive charge, the negative charge will experience as a force, but there will be a torque as well, because there will be some component of force acting on the positive as well. So the torque will act on the system, as well as there will be a net force. So for non-uniform field, not only torque but a force will also act, and the formula for torque is Pe sin theta. Okay, now let's see one problem. This is a problem, basically we have the definition of electric charge densities. I don't want to teach too much about electric charge densities, that is very simple concept. So instead of that, let me solve one question which covers this concept. Okay, a cube of side 2 centimeter has a charge of 12 microcoulomb. So what is the cube of side side 2 centimeter. So side is 2 centimeter, okay, and charge is 12 microcoulomb, right? And you have to calculate the surface charge density of the system. So how many surfaces are there in a cube? First of all, so there is one surface, two surface, 3, 4, 1 is front, 5, and there is a bottom 6. So any parallel this kind of structure will have always 6 surfaces. Okay, what is the surface area of one surface? Say this surface, what is the surface area? Surface area is basically, for one surface, is basically 2 centimeter, that is 2 into 10 to the power of minus 2 meters into 2 into 10 to the power of minus 2 meters square. This is the surface area of one surface, right? So it will be 4 into 10 to the power of minus 4 meter square. This is the surface area of one surface. What is the total surface area? So total surface area of the cube is 6a 1, that is 24 into 10 to the power of minus 4 meter square. This is the total surface area. So what is the surface charge density? Surface charge density symbol is sigma. Okay, line charge density is lambda, volume charge density is rho. Okay, so sigma is basically given by total charge, that is 12 microcoulomb. Micro means 10 to the power of minus 6 divided by total surface area. Very simple, total surface area 10 to the power of minus 4. So it will be 1 by 2 into 10 to the power of minus 2. right? Or you can say this will be 0.5 into 10 to the power of minus 2 Coulomb per meter square. Okay, if you see, none of them have this same value, but what we can do, we can take this point and convert it into 10 to the power minus 1. So it will be 5 into 10 to the power of minus 2 was already there. I have added 1 minus 1, so it will be 10 to the power of minus 3 Coulomb per meter square. Okay, so the answer is B. Easy question. Okay, based on electric charge, again simple concept based question, very simple. Okay, not super difficult, easy question, and obviously you can solve it less than 1 minute. Okay, as easy as that. Now let's move on to the electric flask. What is electric flask? Electric flask is basically given by electric field at a point times the surface area. If you are considering a small surface area of a large surface, okay, so if you consider a small surface area of a large surface, okay, generally we represent the surface by delta S, that is a small surface area, then the flux through that surface area delta phi is basically given by E into delta S. Okay, if they are not perpendicular, if the electric field is not perpendicular but at an angle theta, so in this case the surface is kept at an angle. Okay, so initially the surface was like that, all the electric field lines are passing perpendicularly. Now you have taken the another surface which is not perpendicular, but it is at some angle theta. So the angle it makes with is an angle theta with the electric field. So in that case, the electric flask is given by E delta S cos theta, that is E dot delta S. So basically electric flask is a scalar quantity which is basically dot product of electric field and surface area. If the surface is electric field and surface, they are constant, then what we can do, we can to calculate the total flask. Obviously, how to calculate the total flask? Total flask is basically sum of all such delta phi. Sum of all such delta phi, and we know that at certain cases it is basically integration. Integration is addition, summation, right? Advanced level of summation is integration, right? So it is basically d phi. So this is how you can calculate the total flask, and sometimes we write that as E dot ds. This is the total flux through a closed surface. Okay, you can calculate the total flux through a closed surface using integration. We will use that in our next part, that is Gauss law. So statement, electric flux through a closed surface is given by phi equals to q by epsilon naught. Okay, so this is the basic part of Gauss law. This is the basic part. Gauss law is this only. This one we are using the definition of electric field and flask, the relationship between flask and electric field, to find this one. This is a derived equation. Okay, this is not the Gauss law. This is not the Gauss law. Gauss law is this. Okay, Gauss's law is this one only, but this one is more handy to calculate the problems, numericals, etc. So E dot ds is basically equals to q by epsilon naught. Q here is the total charge enclosed by the surface S. So if you have a surface, okay, S, and you have, say, suppose some charge q1, q2, q3 and q4, q5. This is our surface. Okay, electric field is here. So if you want to calculate the electric flask, flask means the number of field lines passing through this times the electric, basically you can say total number of electric field lines passing through this, okay, per unit surface area. Okay, so that is the definition of flask. The electric flask is the measure of how many field lines passing through this. So in this case, this flask is dependent on here the Q or Q enclosed. Sometimes we mention is this as Q enclosed is basically 1, 2 and 3. So Q1 plus Q2 plus Q3 only. We will not consider these two charges. They are outside the surfaces. These two charges are outside our surfaces. So we will not consider these two charges while calculating the charge enclosed. But you have to remember that this electric field is basically due to all the charges. Even though the flask is due to only the charge enclosed, the electric field is due to all the charges. That is the beauty of Gauss law. Some key points. Gauss law is true for any closed surface, no matter what is its shape or size. So based on this concept, objective questions might come. Okay, Gauss law is valid only for spherical surfaces, only for cylindrical surfaces, only for spherical and cylindrical surfaces. It is valid for all type of surfaces. It is valid for all type of surfaces. You have to understand that. Sometimes they might give you a graphical diagram. Okay, they will say for which the Gauss law is valid. Option A, okay, option B, option C, okay, and they will say all of the above. Your answer will be all of the above. As long as the surface is closed, it is valid. Okay, it does not matter if it is closed, if surface is closed, but if it is an open surface, then it is not valid. You have to be careful about that. If suppose one example of open surface is this, there is no close, no closing. Okay, it is an open surface, just a surface, there is no closing. Okay, so this is just a open surface, it is not closed. That means Gauss's law is not valid for this type of surfaces. Okay, here Q includes the sum of all the charges enclosed by the surface. The charges may be located anywhere inside the surface. This is also very, very important. I already explained that. And the formula for this is Q by epsilon naught. This Q represents all the charges inside, addition of all the charges, right? Charges are additive in nature. Sum of all the charges. Charges can be located anywhere inside the surface, may not be located exactly at the center. Okay, now let's see. Electric field is due to all the charges, but Q is only for inside the surface. So electric field, the formula electric field is for all the charges, maybe inside, maybe outside, but the Q part is only for the charges which is inside the surface. I already explained that briefly as well. The surface that we choose for application of Gauss's law is called Gaussian surface. The Gaussian surface, for example, whatever surface is I have given you, this is called Gaussian surface. Okay, Gauss law is often useful to calculate the electric field for symmetric surface. So this is useful. Okay, so Gauss law is easily applicable if the surface is symmetric, but it is not limited to symmetric surface. That is very, very important to understand. Symmetric surface, for example, sphere, cylinder, okay, they are symmetric surfaces, but Gauss's law is not limited to symmetric surface alone. It is applicable to all the surfaces. Okay, so now few application points to remember. The field due to an infinitely long straight wire, the formula is given by E is equal to 2 lambda by R 1 by 4 pi epsilon naught. Okay, and here you have to remember that lambda is basically total charge divided by length. Okay, so this is the line charge. This is called line charge density, and you can see that it has no R square in the value. It is only R. Okay, so don't get confused here. You have to be mindful about these values. Okay, next is the uniform due to a plane sheet charged, infinitely long charged plane sheet. So in that case, electric field is given by sigma by 2 epsilon naught. Sigma is the surface charge density, so sigma is the charge divided by area. Okay, so they will give you some charge on the some surface with some area is given, and from there you have to calculate the electric field. Might be possible. Now here if you notice that electric field is independent of the distance. How, from where you are measuring, if the sheet is infinitely long, okay, or in some cases even if the sheet is not infinitely long, sheet is finite, but for distances which is close to the sheet, okay, you can ignore the distances. For example, if the point is maybe 1 millimeter or 2 millimeter or 5 millimeter, during that range electric field will be constant. It does not change between the distances. Okay, so electric field is a constant for this case. Now electric field due to a uniformly charged spherical shell. Spherical shell is like the covering of an egg. I always give you the example of egg. If you have seen egg is called egg shell. That is the outer covering. Inside is hollow, nothing is inside. So if you consider a spherical shell which has some charge on this thing, then you have to be careful that electric field inside the shell is zero. Electric field inside the shell is zero because no charges are inside the shell. All the charges are on the surface. So electric field on the surface can be given by E equals to 1 by 4 pi epsilon naught Q by R square. Now very interesting fact is that the same formula we used if we have a point charge Q and the distance is R. Same formula we have used that, and that same formula is valid for the spherical shell as well, but only for points outside the shell. This formula is not valid for the points inside the shell. This is valid for points outside the shell. So any point outside the shell, you can consider the shell to be a point charge. Very important. Point charge located at the center of the shell. This is how you can remember it. But that is only for points outside the shell. Okay, now the graph for this is E versus R graph. As you can see, inside the shell it is 0. That is why it's flat, and suddenly it goes to some maximum possible value. This is the surface. Okay, from the surface it slowly decreases. Again the inverse square law comes back, but inside this it is completely absent. So electric field is 0. So here electric field is 0. Okay, so now if you have any questions, any doubts, please don't forget to mention in the comments below. Tomorrow I will be coming with the live session, so don't miss out on the live session. Also, if you have not yet subscribed to our channel, don't forget to subscribe to our channel. Till tomorrow, bye.